So so I guess probably I uploaded the past exam paper. That's last year exam paper. So you can take a look what kind of style that I would be asking because this is provided without warranty. It means that neither me or TA would answer any question related to that. You just take a look. I mean, we're not going to answer any question related to that. Okay, you can just try, but we're not going to give solution or we'll answer any question. Okay, so just take a look and then you will see what kind of question we have some multiple choice at the beginning, and then some longer question like this. I don't know why it didn't print out properly, but supposed to be something like that. Okay, so this is like some regression tree that you learned today, and then there's some LISO and there's some ORS. Okay, and there's some regression. Okay, so something like what we have been covering. Okay, so the exam will be up to today's material. Next week we'll cover something important, causal inference, but I don't think we have time to cover all that because of the time constraint. So next class we'll talk about 9 and 10, but this class we've just finished lesson 8. 9 and 10 will be causal inference, which is important. And in particular, it will study, right, when you run the regression, right, if you do prediction, like we do today, again, you can put whatever variable that help you prediction, right, and any form will be fine, okay? But this doesn't tell us the causal relationship where Y, or is it true that X cause Y, right? It will be important for business decision, right? I mean, if you want to have a big policy, then probably you need to know those, but that would be it will be very complicated. I mean, usually if you want to do it seriously, you require a econ Ph.D. to do it. But we'll touch the surface and what is going on there. That we'll work a little bit on that next class, but because that part is too advanced, so I just leave it a very scratch a little bit surface of that, and then you have some taste of it. And for today's goal of today will be, we will eventually get into the land of machine learning, where you will learn two particular models, which is the regression tree and random forest. Okay, and then you will be doing in the last assignment 3, will be basically ask you to do machine learning. So basically, just require you to really work on something to do machine learning, right? And that would be the goal. So before we start, probably we should, or very briefly, review what we have done in the last one, right? Because next week will be my last class, and then it will be your presentation, right? And then it will be the final exam. So it's this is my last 2 shows, so I have to make sure that it's okay. So remember the quickly like, so just a review, because in case you are not remember what we have done, okay? And maybe go to the particular slide that is the most useful one, which is this slide, right? That tell us what actually LISO is about, right? And we learned the ORS, right? It's basically sum of the prediction error square, right? And that is actually is minimizing the SSE, right? Right, but if you divide by n, take a square root, is either you say MSE or RMSE, right? Mean square error or root mean square error, right? That is what it's doing. And the LISO is just basically the same as before, but we add a penalty for the size of coefficient, right? If the coefficient larger, then you don't want that happen because we're minimizing, right? This alpha is positive number, right? Is the larger the alpha, the simpler the model is, right? So your choice of alpha will determine the complexity of the model, right? The higher the alpha, right? If the alpha is super large, then basically all beta are close to 0, right? So that would be the main idea, right? The controlling the complexity parameter alpha, you decide how deep the model is, and how to choose the complexity of model, right? Is by choosing the one, is searching for the one that is minimizing the whole thing, right? Right? So minimizing this part, right? MSE, right? So basically you just choose this, adjust, so that the first part would be the smallest, right? That's what we have been working on, right? Using the CV, I think we did that, right? I think, did we did that? Let's check. Yeah, we did that. So we choose the LISO, right? And that's the best RMSE, right? Is the lowest is, I think the lowest alpha is 0.7, right? So there are many alpha you can choose, and the smallest one alpha is 0.7, right? Which gives you the lowest one, right? And do remember the way we do this LISO has no theory, right? Just purely modeling. Just data tell us what it is. Okay. So that is the main idea behind LISO. Just you have to give me everything you think is relevant to the model, where you need a square term, you need to take a log, whatever you think the transformation you want, you put there. Okay, and then the LISO, the algorithm will choose which to keep. Okay, and of course, besides alpha, one of the practical things that you probably also you remember is what you consider 0, right? So you drop those variables. So you just effectively are saying that to what that common places, you keep them. Okay, I mean in some sense, right? Because you want a simpler model. That would be the idea of the LISO. Okay, so basically control two things: the alpha and what you consider the cutoff to be 0, right? Effectively, right? Because you want to keep the simple model, so you drop those, right? That's how you drop from 300 to 70, right? So we just keep around 1/5, 1/6 of that. Okay. So that would be the LISO. So what are we going to do today? I guess it's the important lesson is as we hinted, we'll do a regression tree random forest. Okay. So it just exactly opposite the LISO idea. LISO is you have determined, you tell me what is the biggest model you can do, and the machine will tell you to reduce it. Okay? So that's from big to small is what LISO do. And what regression tree and random forest is reverse. We start from scratch, nothing. Okay? We successively, one by one, we add things into the model and see how the model improvement works. And we add until there's some desirable criteria being reached, and then we stop. So it's just like it's doing addition here, right? LISO is doing subtraction. You take away things, okay, to see how doesn't change the improvement, right? It's just like you have a very big model, you take away stuff, and see if the prediction error still remain a reasonable range. And here is opposite case. I have no model. I keep adding things, and then add until, but there shouldn't add things there. Okay, so that is the way we do. Okay, and let us talk about the machine learning. Okay, so just very briefly, right? The regression is everything done by human, right? You have to decide what the model, you do the best model, right? You run the horse race, you have to decide all the regression equation. And LISO is just, you don't have to tell me what's the best model, right? Just automatically the thing will tell the model, right? Because you give the biggest model, the minimization, the alpha will determine what's the best model there. So that's the part that is there. Machine will choose for you. You don't have to physically pick which one. So the last one is even more easier, okay? We just need to select what the variables. We don't need to decide what the functional form. We don't need to worry about square, cubic, or whatever, okay? It's there, okay? You don't need to think about transformation. It will be done for you, okay? You don't need to worry about grouping anyway. So before we say, okay, we have to group, okay, from 1 to 3 is one group, 3 to 6 is another group, 6 to 10 is another group. But for machine learning, we don't have to worry about that. Or everything, just tell me the variable, automatically the computer will do everything, okay? Of course, you still have to worry about missing data, right? Missing data, you still have to do things, right? But otherwise, machine will figure out what are the models, okay? What are the solution is given by them. So basically just clean the data, everything is nice, then just machine will do everything for you, okay? So that would be the thing. And so the procedure is actually similar to what we have been doing, right? You have to divide data in two parts. One is a training set, one a test set, right? And the training set will fit the model, and then you, based on the test set, to select the best model that we've been doing. So this is something we have done many times already, so I'm not going to go into detail. And as I said, we focus on two particular methods called CAT and RF, right? And we will be more or less informal in terms of describing algorithm to estimate those. Unlike LISO, we tell you how to do it. We'll just remain verbal. The reason is being, if those who want machine learning will actually study the machine learning class next semester, or next trimester. So I don't want to repeat too much because I guess a previous cohort complained that courses have too many overlapping material. So I try not to talk too much, but to those who don't want to do further machine learning, so this gives you some idea what we're doing, and then you learn a more formal one. And anyway, now internet is so convenient. If you want to look further, this is easy, right? But I just give you the minimum thing. So what are they? We'll do it before the break. Is to give you idea how to do the tree. Is based on what we call binary split. Okay, we'll do cut. Okay, every time. Okay, what do I do cut every time? Actually, that's what we have been doing in the. Just let me draw a diagram. So if you remember, there's a we've done many times. It's called the with x and y. Just for simplicity, focus on the case we have y and x. Okay, you can generalize to more than one variable, but the idea is there. Okay, the idea is, you remember we do the hotel data, right? Hotel price data, where y is the price, x is distance to the center, right? And the data looks like this. If you still recall, somewhat like that, right? Okay, the somewhat data like this, right? The further away from the center, the price drops, right? And then we said one linear regression may not be good. We need a contrastive term, right? Or separate into two parts. We run a regression. There's many ways to handle this nonlinearity, right? And but before we run regression, we one very important thing is we call the bean scatter plot, right? And what we said is, okay, we decide what is far away, what's close enough, right? We said that, okay, and what we do is, okay, is 0 to 1 is one group, 1 to 2 is another group, 2 to 3 is a group, 3 to 7 is another group, right? And the bean scatter plot will tell us, okay, this is the mean of this part, this is the mean of this part, this is the mean of this other part, and this is the mean of the part, right? So that would be the model that we have, all right? So we have to human specify what is the grouping, okay? And then within a group, we create the average within a group. That would be our bean scatter plot, right? We call that actually a non-parametric method, right? Because we were not estimating anything in this model where data tell us what they are, right? So, and here we actually, the regression tree is very similar to this one, okay? So let me try to draw another picture, because that would probably not to confuse you. Another picture, the same one, but I tell you how the regression tree works, okay? So it will be something like this, same as X and Y here, okay? And let me use the black color for the data plot so that you know what's going on here, okay? Something like this. Okay, this data, right? I hope still recall this data, okay? Because you have worked on the assignment 1 and 2 is like this, right? So I hope you still remember. So assignment 3 will be different data set, okay? But because that one is not good for machine learning, so I would ask the TA to check the assignment and they'll release to you later, maybe next week. And this one, okay, how do we do tree there, okay? The tree is the following. As I said, we do bisection time by time. So what we're going to do is we have to find a cut. The program we have to figure out, okay, which the data would do is we'll do a cut here, okay? This cut will be determined by the machine looking at what? Looking at this. Okay, suppose I cut here, okay? What are we going to have is, remember the bean scatter plot idea, okay? You calculate the mean of this Y, right? Mean of this area, give you this number, and mean of this group will give you this number, right? If this is our model, we can calculate the mean square error, right? Looking at each point, the vertical distance, square some of them, okay? And machine will tell us where the location of the purple is. So the machine will tell us the grouping, the first grouping. If you want the simplest tree, this is it. So, okay? But this is not the end of the story. We have to go, if this is a tree only have 2 branches, it's not fun enough, right? So we will do is, we keep doing this, say, now this is the first group. And then we will do another grouping, okay? Instead of this, we will be grouping in this one, okay? We're asking within this group, can we do another subgroup, okay? The subgroup means that I have the red here, okay? The red, of course, we choose it optimally to balance the 2 choices, okay? Which might be, use the deeper purple, yellow, no, green, maybe green. So within this group, the mean is here, right? Within this group, the mean is here, right? So what I do is try to move the red left and right so that the mean square error, according to this left part, is the minimum. You do the thing for this other group, the same here, okay? You do the same for the other side, okay, maybe other color, like here, right? Then you will do the green part maybe somewhere here and somewhere there, right? Somewhere there, right? That will be our model, okay? So you keep until that there's some, maybe there's 2 failed samples left over, there's some reason you stop, but this is the way that you build a tree is you have the whole pieces, you cut it, and remaining pieces you keep cutting it, okay? So that is how you run a tree, okay? It's successively choosing the grouping by the machine. So the machine will learn where to cut, okay? You are not, the bean scatter plot is you decide what it is, okay? And here we don't, okay? It's letting the machine to decide. So here, if you cut in this way, here you may cut again, so you will keep cutting, okay? You keep cut until that you have some desirable property, you tell it to stop, okay? So that would be the main idea of the tree. Is that clear? So basically it's bean scatter plot, but you are not deciding the group. The machine will tell, of course, with some criteria you set, it will stop somewhere, okay? So instead of you decide what to do, you set a criteria, computer follow instruction to tell you the best cut, okay? I mean, it's not saying the machine is better or human is better, right? If you know what's going on, right, like the distance, right, then probably human is better. But if you don't have, if no knowledge, their machine is better. The reason why is this is because you're IT manager, right? You have a large set of data, right? And very often, very likely, many columns, none of the column will be very important, right? The joining is very important, but by themselves may not be very important, right? Just like you look at the website data, right? You look at how many people click on the first button, right? How many people click on the second button, right? How many people click the like, subscribe, and share? How many people wait for how long, right? You have all the details of how they interact with the website, right? And then maybe each element is not important by themselves, right? But combined is important. So you don't have good knowledge about what to include, not to include, right? In that case, machine learning will be very helpful to tell you some story, what may be behind, and then the machine learning is not end of story, can help you to do actually write better LISO, write better regression. Okay, so this machine learning is not the end, right? Regression also not the end, right? Regression actually can help you to think about what should be in the machine learning thing as well, right? So it's not something that, I mean, they're unrelated, they're interdependent. Okay, you don't need to stick to one particular methodology, right? You can jump around to see what to improve your methodology. Okay, so I hope this is now it's clear what we're doing. So let's go directly. I mean, before at the end, the random forest is actually similar to the tree idea. We'll talk about that later, but the main idea is very simple. Tree and forest, you know what does that mean, right? Forest has many trees, right? That is exactly what it means. And what do we do for the forest is the following. The main drawback later you will see, the tree is very sensitive to outlier. If your data has something where weird thing happen, the tree can change drastically. Okay? So random forest later you will see what they do is bootstrapping data. Remember bootstrapping? You based on data, you create multiple universe, right? And then for each universe, okay, you create a tree. Average of this tree will be the random forest. Okay? For random, it's because the part that you selecting the data, you create multiple universe, right? And that part is random, right? And also there's some other random stuff there, but the main idea is why we do that, because tree will likely to overfit, right? When you bootstrap the data, you create multiple universe, you just avoid that feature there, right? Because you're selecting data from there, right? And then you fit the tree, okay? And that will be the idea, okay? But later we'll talk about more, but this is the main thing we learn, okay, today. So just say, as we said, right? And we just said, we just let one variable, but you may ask how we select more than one variable, the same idea, okay? You would start from one variable, you do that, okay? One variable x, you do that, you tell me what's the best cut, okay? And you go to the next variable, what's the best cut? Until the end of the variable, what's the best cut, okay? Then there are many, you have n variable, you have n different cuts possible, right? But you don't cut it, right? Then you choose the best one to cut. Suppose variable number 3, you cut in that way, okay? Then that means that your data divided in 2 parts, okay? And then you do the same procedure, right? Choose which variable to cut, okay? And that you cut is basically you cut the data into many different groups, right? And then at the end, the average value of y in this group will be your prediction, right? It's a multi-dimensional bin scatter plot, right? Same thing, right? But now the cut will be organic, right? Depending on data. So cut can be very weird, right? But before you learn, if you do bin scatter, if you decide the cut will be very vertical, right? Now the cut can be any very weird shape, depending on how you cut, okay, the data, okay? And this cut is step by step, okay? What do you mean by that is, we don't care about the future. Every time we do the cut, we care about the current data. We do the first cut. And after that, we separate the two worlds already. Look at this only part they do the cut. Okay? There's no relationship between the two dissect apart. Okay? And the first cut and second cut are unrelated. Okay? Because the first cut is the best, the second part is the best, but you don't talk about how to do these two cuts in the optimal way. So it's like a myopic or the greedy algorithm. Okay? Every time you cut, you just care about what you see right now. Okay? So you're not forward-looking. So let us have some terminology, because that will be something that we need to discuss, and then that will be useful. So the top node is the one is important, the very top one. And the terminal is the ending one. And all the ending node we call the bucket, okay? And the stopping rule will be when to go to stop, because you can keep cutting, right? You have to tell me when to cut. And it's important to cut earlier, because you want a simple model, right? Because if you have a complete model, you overfit. Remember the RMSE is a U-shape, right? When we go to live data, right? That means that you don't want to cut too many, right? You don't want to cut too much. And the tree, right? The branches will be mean how a node send out to the other nodes, okay? And cutoff point will be later. You see how we cut the branches. And the size of tree will be number of node plus one. So just name. I mean, it will not be very useful for our purpose, but if you learn machine learning, I mean, you have to know this terminology there, right? Because machine learning people, they use very different terminology than people who do regression. But just let you know the name. But I'm not interested in asking terminology, but that's there. Okay? And as we said, right, we will do there's no formula, no coefficient. Okay? And there's a tree there. And then look at all the cutoff and then find the smallest. Okay? That will be the goal. So let us look at the example. Okay? We skip this technical slide. So this is the most, I think, the simplest example that you can imagine. Okay? I have X has only single variable. Okay? 1, 2, 3, 4, 5. The simplest you can imagine. And Y, the predictor, have 5 value. 2, 4, 4, 2, 4, 5, 4, 5. Okay? And when I want to do a tree, it's very simple. I just use the machine learning package, okay? Tree package, okay? I use the decision tree regressor, okay? And there's only one thing I tell him to stop, okay? There's a option here is maximum depth, means that I only cut once, one layer of the tree. And I fit it. Of course, this one can change, but you can change whatever number there, but this simple model, I can just use one. Okay. And this is done already. Just one line. It's very simple, right? The Python code. 1, 2, 2 line. Okay. If you like, you can just do the fit. At the end, it's one line, right? Just basically one line code. There's nothing new there. The estimation is very fast. And you can say how to plot the figure. Usually, you need this figure size to make it look bigger, okay? This is the width, this is the height, okay? And then you tell them what the tree, what the feature, and then fill the color, and then title, okay? So let me run this code, because I guess that would be important to run with you to know, to let you see how we run this. So this is the code, okay? Just wait, I think, a few seconds. You'll come out, let me clean the... So it takes some time, right? It's not super fast. It takes 10 seconds to run this. Even this is very simple code there. So to see the tree, okay? One level tree here. So the first thing is to ask one thing. Okay? Here the tree is here. Very simple result. The tree have one cut. The cut is at 1.5. Ask ourselves, less than 1.5 or more than 1.5. The model will tell if less than 1.5, okay? This is top node, this is terminal node. The terminal node tells us the value is 4, okay? Which means that if your prediction, the model is like this. Now the model is like this. We have here. Our model is like this. X, if X is less than 1.5, okay? Our prediction, Y is 2 here. Okay? And what happens more than 1.4? That's false. Okay? That is what we said is actually 4.5. So our model predicts 4.5 here. This is our model. Okay? And if you remember what is the data, it's something like here, right? 4, 5, 4, 5. Okay? So that's the data, right? That is actually our regression tree tells us this is the model. Okay? And the 1.5 is they choose using that data, right? So this is a regression tree. Okay? Is that clear? If that's okay, let me continue to work out the rest. Okay. This is the model. Now, if you want to do prediction, as we said, right? So if you give me phi number 0.5, 3.5, 4.5, you want to predict. It's the same as before. Dot predict the data, and output, as we said, is 2.5. This is what we have said, right? Because the model is like that, right? So I think we did that, but I just run it in case you want to see. I will do it quickly because I don't see this is something terribly important here. This is just telling you that P0 is set, right? It's just because of the thing. Look at 0.5. This is true, go to here, right? And this 3.5 go to here. 4.5 is go to here. That gives you 0.5. Okay? So I hope this is clear what we actually are doing. Is that okay for the tree? So now you understand that we are going to go to the application, and we will draw a much more complicated tree. Okay? And then we look at our regression and compare to our tree. Okay? We will show that tree is better than regression, okay, in prediction. Okay. Now, remember this data, right? Car data we have done several classes ago, but let me do it quickly. Download the data, right? If you still remember this data, it's a second-hand data. I think in UK or I think in Chicago, in US, and what they're trying to do is looking at the second-hand cars and look at different features and use that feature to predict, right? I think we run a regression model, right, to that, okay? So this is data, and then we focus on Chicago, and then we focus on auto car, not the truck, not new, not old, something like that, right? So this is the data cleaning. So once I clean the data, I think we know that. I'm not going to repeat that, okay? And then I take out the outlier, okay? And I want to remind you one thing, as I said, regression tree by itself is very unstable when you're outlier. So that's why this part is very important. If you want to do the right thing, this is the one. Make sure that your data will not be a lot of outlier. But the problem is outlier, you have to use your own judgment to say what is outlier, what is not. So that means that the domain knowledge is important, right? So that means that you have to be very careful to clean your data. Okay? And here we have, and the last thing is to have the condition of car, which I think which should be fine. Okay, so this is the one. Is that okay? I hope you don't have problem of copying. There shouldn't be something too terrible, right? Just copy slide by slide. This one, okay? And this one is the cylinder, which is the last one, I guess. And then we have some square term, and that's it, okay? Just bear with me for one more slide, then we go to the real thing, okay? And this is cylinder, right? We'll do that as well. Okay. And once we did that, let's forget about this. So this. And then with the cubic term, for us, I don't think we need this one, but I just keep there. I don't think we need that one. I don't think we need a square term because that's the reason why we need regression tree, right? Because no square term is needed. So just forget about that slide. Oh, I know why we need it, because I think we compare regression. Do we? Let me check. No, we didn't, so that should be fine. I think it's okay to not to include that. Okay. So here is the important part is to drop the, because we want to predict the price. So if the price is not there, right, we should drop it, right? We should keep those things not NA. Okay. And I reset the index to make things nicer. You don't have to do that. Now, before the break, I want to show you a tree because it's a real data, right? And I start with the most basic model. Just use the tree by age. Okay. So how do we do that? The same thing here. Okay. The only thing I think is a little bit slightly thing is I need to use the double square to get the matrix. There's some tricky part there, but otherwise, other things are very straightforward. Okay. So this is the same, right? I run the regression and okay, and run the tree. Okay. So you can see it's very simple, right? The code regression tree, and I tell them how deep is the tree, okay? And I fit the model there, okay? And now, once I'm done, I can plot the tree, right? This is I fit the model, and I ask him to plot the tree, okay? And when I do it, okay, it's very simple. This is my model, okay? You see, maybe the height is smaller because I seems to be a little bit too high. Okay, this is a good one. Okay, so here we have a model. Maybe you can see it's very simple. Less than 6.5 with this. More than 6.5 with that, right? And the value will be, if your car is less than 6.5 years old, the price you should sell is $13,542. If your car is old enough, then you sell it $4,400. So it's the most simple thing you can do, right? Right. And then this grouping is determined by data, right? The good part is the data tell us 6.5 is cut off. 6.5 is how old is old, right? It's not something like we have predetermined idea how old is old, right? Not like you are below, you are born in 80s, 90s, and 2000, right? 你不会说80后、00后、90后, right? It's a cut off whether you call it old, right? There's a formula there to call it old, right? On data, If your car is more than 6.5 years old, it's considered old. Okay? Of course, this is the one level tree. We'll talk about more complicated tree after the break. But I guess now you're pretty happy because I think we have the real machine learning code run once. I mean, if you haven't run before, this is the first machine learning code you have ever run. Okay? So let's a break of 15 minutes, then we can come back and we'll do more complicated tree and draw more diagrams, and that would be cool. Okay? So in the meantime, let's a break of 15 minutes, and then we come back. During the break, you're very welcome to write down your comment and question. We'll resume at 10:33. Okay? I'll see you then. So maybe you look at how your response so that I can see if I can say something. The final, as you can see, maybe I just go over it quickly again. So it's not computer. It's like you just bring your pencil and paper and your, if you want, you can bring your calculator, but I don't think any calculator we need, right? But if you worry about that, but you'll be something like, okay, calculate mean, median, mode, right? The basic thing, right? That's the case, what you get, and coefficient correlation, some calculation. If you want, you can use calculator, right? And hypothesis testing, all right? And some confidence level, right? And what are the tests we should use, right? And whether you have binary data, what you want to do, what is the difference between regression tree and random forest, what is LISO and regression, what's R square, right? Those something similar, okay? These are the multiple choice question. Of course, last year, I think someone reviewed my question paper. They said it's slightly too easy, so I will increase slightly a little bit some of the question, but I think half of the question will be at this level, and half the question will be slightly little bit more difficult, but I mean, shouldn't be an issue anyway. I mean, just to differentiate better student, but I guess your grade overall, the discipline will be the same. Just, I want to have some dispersion, I mean, but I think the people who get A and A minus will be the same, okay? But just, we want some better reason why some people get A, some people get A minus, but rather than that, I mean, there shouldn't be a big issue there, okay, for you guys. And for long question would be something like, I'm not expecting you bring the computer, so that's why the code, I will give you this, okay? And I run the code for you, then I ask a question there. So you don't really need to, you don't have to compute this. No, this code is there, I run that for you, I'll be there, okay? And all you need, right? You don't need to know the code because the code is already created for you. Maybe I ask you what that code does, but that will probably, you don't need the coding, right? You just need the computer, right? And then that will be the question, right? Say, what's the model based on this? You write that down, right? Y is equal to blah, 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 right? What coefficient and confidence level, right? And what R square, what does that mean, right? For prediction, right? Same when you, this is the logic, and this is the LISO regression. This is what you see, right? And what the prediction model, and this is the regression tree model, as actually similar to what we have seen, right? And then what the output, okay? And just one thing, as I said, right? Last year, people review my exam, say it's too easy. So there will be at least one question will be more difficult than this level, but other will remain the same. So maybe 3 questions, 2 questions will be same as this level. 1 question will be a little bit more difficult, maybe some open-ended one, but to see whether you know the concept really well, but otherwise, similar level you expect there. So I think last year, I think most of the students actually, majority, I mean, more than 70% get very good grade. I mean, maybe 80, above 90, right? And that is no dispersion, right? Because most of you actually get very good grade there, and that's why you need to add something there. But I guess it's if you're good, you should be fine, right? Your average also fine. Just don't worry too much about it. It's open book, right? So I guess it's like I think it's a 1-hour exam, right? What we have is, so it's not something like, I guess it's, if I give you 3 hours, 2 hours, you can really do it, right? But the point is whether you can do it within an hour is a little bit more challenging. That is the challenging part. It's not the question how difficult it is. It's rather how fast, whether you can do it. If you don't know, you take time to look at it and you don't know how to do it. So that's it. I mean, the material in our class is not very complicated, right? It's understandable, okay? So, but to differentiate how good you are, I ask some challenge question, like open-ended one, right? Say some conceptual one. That would allow me to take off some of the mark, right? Not everyone got 90 above, right? So some mark we deduct, some people get 80 something like that. So that would be my expect, right? You should able to, but to be honest, right? If I give you 2 hours, you can finish everything. Shouldn't be an issue, but I'll give 1 hour, so that, I mean, if you know, then you can get 100, right? If you don't know, you can get 80 something. So that would be there. That would be something like that, okay? But to be honest, I mean, you're a master student, right? So I guess the grade by itself is not super important anyway, right? I think the more important is to get a job, right? So learn the skill there, write down your CV, you know how to run this, how to do the project, that would be great, right? So I guess in the presentation 2 weeks later, right? I think you do the group project, then I guess I learned from other class, right? We probably would like to vote for the, within our class, right? Vote for the best project group, right? And then also vote on the best presenter. Then you can write on your CV better, right? And then that would be help. I mean, or you can tell me what kind of the prizes you want to put there. We can vote then, right? I can sign the certificate, right? And then you can put in your CV, and then it would be nice, right? The best presenter in this class, right? The best project, and so on and so forth, right? You can tell me what are the name that you want to add. We can do that. Okay. Cheat sheet, whatever. You bring whatever, how many you want. Just you can only bring the printed copy, but not the computer. The reason is beyond that the possibility of cheating, and there is actually some people actually discuss how to cheat. So that's why it's reported, and then that's why I can't allow. Okay. So the reason is I intend open book, open whatever, right? I don't care, right? But the problem is like that. And also ChatGPT, right? So makes if I allow computer, then I have to make the exam very difficult. Probably you don't want that, right? So better not to. Are they good? I think they can be better, to be honest. But for our class, because I think they're better in the sense that I think it's like too technical, the report. I think they can be more business, the one I saw, right? I mean, it should be the business class, right? The business school, so I would expect more business-oriented. Tell me exactly what it is, right? And skip the details to the appendix, tell me the main thing there, right? Don't expect people, you go out, right? Don't expect people to have even more than 1 minute to read your report. Maybe 1 minute you can capture the attention, that's it. You can't, then you just out. Just like go to a job, right? Go to the interview. If you can't impress the interviewer within 1 minute, then you're out, right? Because look at the CV, also the same thing, right? If you can't capture their attention, then that's the end of the story, right? Like my teaching, right? You're here, right? If I lose you 1 minute, then you just look at Xiaohongshu or play a game, right? So I want to make sure that you pay attention, right? So, but that I hope that answers your question. But of course, I think you can tell which one is good, which one is bad, right? I mean, which one is better, right, compared to the example. But I upload all the things, not examples. So I upload the full set, the full sample there, so you can tell what's good, what's bad, right? You can tell, right? Of course, different people, different tastes, but I think you can tell which are better one. Good. Hopefully everyone got it right. Yes, that's good. Yeah. Today is sunny, also windy. Surprisingly, this morning the temperature is 20 degrees Celsius, but now it's like a little bit hot, surprisingly. Yeah, regression tree, machine learning, DOTE. What's that? No. So far, everyone can follow. I think it's okay. That's a good sign. The speed is okay. I hope you don't give up this class, right? None. Yeah, tired month. Well, it was very tiring. I think for everyone, it's close to the end, and hopefully, I mean, this class is our almost last class. Next class is not including the exam, so I hope you still attend the class, right? But It's very tiring. I mean, especially you have to trimester, right? You have 3 semesters there, but it's a little bit tiring. I hope you stay awake like me. Coffee can help a little bit. Well, the good thing is if you think about that after a few years later, think about your life in CHK, you think about getting tired is good. Okay? I mean, in tired you learn more than other than after this intensive 1 year, then you go to work. If you don't go back to school, then this is the last moment for your school. Other than you can't come back to here to learn, because when you work, you have to learn all the time. Now is the most intensive time, so treasure it. Unless you like me, go to the Ph.D, right? Willing to earn less, otherwise this is the last moment you learn, formally, right? You go to work, then the boss gives you this, you have to work it out. Okay? It's not something like you have the TA to ask or teacher to ask. No one will teach you for free outside, right? But of course, you pay for tuition, right? But it's different. It's a very different story, right? Outside people will not, right, teach you like in this way, right? You have to learn. So I hope you just use the time to learn more, because this is the way how you train yourself. Okay, so let's continue. We have the tree there. Okay. Yeah, this is a tree. Someone tell me this is different from the tree I drawn. Probably this is a tree I drawn from the old data. The data is different, but anyway. Why is it? Okay, maybe the same data set, right? I think that. Let me see. Okay, it's slightly different. Is it the reason that is the random? Let me check. It can be the reason due to the fact that I have different random state. Yeah, so yes, except no, not really, because the random state can affect where you search, right? Because you're searching for the cutoff, so it's not actually, right. As I said, they look at the cutoff. It's not really from 0 to 100. They look at this. You will take a very long time. So they randomly pick up some number. So the initial number pick is a random number, the random state, and that actually can change the solution a little bit slightly, but usually it's stable. Okay, but as I said, right, it can be really rely on where you start, right? Because the optimization, if you know, right, can be locally maximum. So depending on where you start, you can stuck there. So may not be straightforward. So that's why. But we also usually set a random state so that we can replicate the same thing again. So, but just a minor footnote there. Okay. And you can compare the data, right? That is, we don't look at tree, but this is not so it's easy to look at the answer, right? But when the tree is complicated, then we probably want to plot what I have just drawn on the whiteboard there. So that's what I do is, I want to draw a scatter plot, right? So that's what I'm doing. What I do is I create data frame X, okay? That is based on the maximum age and minimum age, and I do 0.5 interval, and I do the prediction there. And once I have that, I want to plot them. So I have a scatter plot based on original data X and Y, and the plot I have is based on the generated one, right? This X is the all possible X. The Y will be the predictor based on the tree, and the red color, okay? So let me do it with you, okay? And let me quickly. Okay, if you run this one, so you will see this is, as I said, is the bin scatter plot, right? Here 6.5, this all average is here, this all average is here. So this is the plot. So this is one. This is also good for presentation, right? When the tree is very complicated, this is the best one, right? Because no one is going to read the whole thing, right? When you have only one variable, right? This is easy, right? But when you're more than one variable, it's hard to present this way. right? But this is a very good idea what's going on there, okay? And to continue, okay, let me allow 2 levels, okay? Still age and 2 levels, and you will see what's going on there quickly, right? The only difference is here. The maximum depth is 2, okay? There's nothing new there, right? Before it's 1, 3, 2 is 2, okay? So allow the tree to grow 1 more level. So instead of 1 cut, I have 3 cuts. Because first cut I have 2, and cut more, 3 cuts of data. Okay? The maximum is 3 cuts. So here I just feed and plot, right? Just 1 slide. Just 1 bunch of code there. Okay? So if you do that, maybe I have to make it bigger because this is a little bit too small. Just remember this plot figure, you put in there, then make this look a little bit less harmful. So I hope it's clear now. So you will see the first cut is 6.5, the second cut is 4.5 and 12.5. So it will be 3 layered. We'll draw it, but you will see if this is youngest, you'll be this value. Second youngest, this one, third youngest, and fourth youngest, right? So this is, you can look at that, right? So to make our life easier, right, it's good to plot what we have seen, right? So the same code here, there's 2 here, right? The same thing, the same code, we'll just run, okay? And after this, we stop a little bit to discuss what we have just saw. In case you want to, I hope I didn't run too fast because I tried to run the code with you, and hopefully that you will feel less intimidating if you never run a machine learning. So this is you will see because I have 2 levels, that means I have 3 cuts. So that's why I have 1 cut, 2 cut, 3 cut, and 4 levels, right? So exactly this is the model, right? It's better than we decide what is it, right? Because remember, this is, if you run a linear regression, the set may not be fit very well because this part will be flat, right? So maybe if you want a regression, you want a square term, right? So maybe fitting better, right? But y square can be cubic, can be whatever, right? So we don't know. So the good thing about regression tree you can see is I don't need to decide how many cubic terms I need to remember, right? Just let the model decide. You tell me how complex you want, which is the number of level of tree, then you can fit it. Is that clear? So here I still remain 1 variable, explain the price by age. So we want to do more, right? So here's the thing. But before we do that, this is the model. We want to do a little bit more fun first is we want to do ORS or compare ORS and tree and see which one is better, right? Because it's the most important part, right? We want to compare human and machine. ORS is machine, sorry, ORS is human. But tree is machine. So we want human versus machine, okay? And how we evaluate? So far we are looking at the whole data set, right? Right? We are not doing the test string split, right? That means that the fit is not clear with good or bad. So what we'll do is we will use the validation idea. Okay? We'll cut 20% of the data, run a training, either ORS or regression tree, and then look at the RMSE based on the feeder model and see which one wins. And that is the preview. ORS give us 2,300. If you have 3 or 1 depth, it's 2,900. So ORS win. Okay? But if you have allowed 2 level, 3 wins. Okay? So that means that because 3, you take care of non-linearity. Okay, much better. Okay, but let's run it quickly. So what we're going to do is use the model selection test string split we have seen already many times. Okay, and you have x and y. and you separate them based on X and Y. Okay. Of course, you can have a data set and then split it and then assign what's X string, Y string, or the same thing. But I just do it this way. Okay. So you define what's X and Y and split, or you can split the data set and then you can assign what's X and Y, the same thing. Okay. So it's up to you what to do for this one, but I use this one. So I just copy that. So here means that I have 4 different things here. Okay. And I use 20%, right, as the way that I do the division. Okay. So I track, test, and train there. And now I want to do all rest, which is something simple, but what I want to show is because of we're doing machine learning, and the easiest package to run regression, not to do analysis, just for prediction, is using the linear regression package from the machine learning package. That will make our syntax more uniform. Okay? And this is only good when you know X and Y to run. Okay? And later you will see, I mean, because you can't specify the equation, right? So you use everything in X. So that's why this is good for machine learning, right? But not good for comparing regression by themselves. It's better to use a stat model if you want to purely run regression. Okay? But we now know only X is just one thing, so this is okay. Okay? So what it do is run the regression, fit the model, do the prediction, calculate the mean square, take the square root. That's RMSE. Right? So just copy the whole thing. This is the regression RMSE. Okay, we are doing the. So we can print that out, right? RMSE. Okay, and see what RS is. So as we expect, 2300, right? We have said already. Okay, this is the horse racing outcome. Simple linear regression. Okay, and now we have the tree. I think we have seen that already. So the same syntax, right? So that's why the machine learning code is very simple. You just change this guy, and do another model, right? So it's very convenient. No matter which model you're doing, just change this guy, right? You compare to this one, just this guy change, right? Do the same thing, right? So I have the model of tree 1, okay? And we probably want to look at the outcome as well, right? So just this guy just here, okay? And see what's the outcome there is 2,900, okay? So it's not so good, right? You say, okay, well, we do 3, right? But when you go around and do the, oh, sorry, this is a duplicated slide. Do the level 2 there. You will see that, oh, I can print that out, sorry. I should print that out. So you print that out, it's 2,100, okay? So you will see the tree is better than regression, right? Even if you have just very simple example, right? Of course, you can do the comparison table like this. You create the data frame that print that out, then you can do that as well. If you want to look at better looking table, that's what you will do, right? So you see, this is comparison here, right? So you pick, if you want to do the simplest case is you do the RMS. Based on RMSE, you do the tree of depth of 2, rather than regression. So illustrate that, I mean, when the model have some nonlinearity, right? So probably you want to consider a tree. Of course, I didn't try the ORS, the square term, so it's not fair comparison, right? But at least you can see if you don't know how to take square or you don't know much complicated, right? Potentially, tree can be better. Is that okay? Now we have more fun because so far we just only compare one variable, right? That's not fun enough, okay? So let's talk ourselves into a more decent thing is, as I said, when you have many variables, you do the same thing, right? You just choose which variable to cut, right? And then let's look at the used car data, which we use the most complicated model. If you still remember, hopefully you do, the model is like this. The price is based on age, is how long the car has been there. Odometer, which is how far the car has been traveled, the real age, right? And LEX, LESC is the type of the car. And condition excellent or very good is dummy variable. And cylinder 6 is whether the car has so many engine there. And whether it's dealer, right? These are all variables that this is the best linear regression model, right? And then with the equation there, then what we want to do is to get the features, okay? Because that will be the thing we needed. What we do is look at this model. We split by this snail, okay? We call 1. Snail 0 will be the price. Because look at the snail, split with snail. If you take out the 0, it will be the price and a space. If you take the 1, will be the one that after the snail, right? And the huge you will be like this guy, right? It will be this guy, it will be this guy, right? And then the features will be I split by plus, so it will be age, odometer, this kind of features. Okay, that's why I have to actually can do split 2 times, but that is you can actually, if you are good enough in Python, you can just put there, right? Usually, but I guess Python, the idea is clarity is more important, right? When you write programming, so that's why I do it step by step. If you're expert, you can just right one line you are done, right? But you will see my code is not very efficient. Okay, or write the code, but I try to write the code that is more transparent. I think that's more important than look cool, right? I mean, and here is I have to remove the space in there. There's the feature names because I don't want the space because when you cut by that, you will keep the space there. So the feature names will be that one. So I want that, okay? So this is nothing, but I just extract the names, okay? And the equation. Later I run the regression, okay? And also the learning code will be there. So this is preparation. Okay, we are going to do is first we'll do the test string split. I use 70% to train, but you can do the 80% or whatever, that's fine. Okay. Here I decide the train size, but you can also do the test size. I'm not using the unit. You can use the test or do the train, the same thing, right? Just 1 minus. But here I do the train. So here you can see I divide the data set DF, not the X and Y, but the same idea, as I said, right? Either you do the DF or do the X the same. Okay. So here I dissect the DF, right? But also you can dissect X and Y, the same thing, but I think that is easier. Okay. Once you have that, I'm going to fit the model, okay? And to fit the model, I actually require us to tell me what's X and Y. So we'll use the past SY from D matrix. That's what we do is D matrix model. That's the model. It's very good. Automatically, you give me the data set, you tell me what is X and Y. So that is very important package there, right? Because the equation, there are many variables, and then we tell them which one to pick, right? And this already, the D matrix, the data matrix already gives you the matrix. It's a very nice, well prepared, you can run your code there. Is that clear what we are doing? Right? And then I use the maximum depth of 3. You can use any number, it can be 4 or 5. I make it 3 because I want to make it look nice on my slide. Actually, 3 is not the best one. But of course, one of the questions you have in your mind is this one actually good, right? Is it good to limit this guy? We'll tell you more, but this is the parameter. Usually 3 or 4 would be the best because you have too much, then probably not very good. Okay? But in practice, if you ask, you can do a cost validation to figure out this one, right? But we'll talk about that later. So here is, I take the train data, right? And dy was x plus and y. And I run the regression tree here, okay? And after I run it, then I can display what it is, right? This is the most important part, is to plot the tree, okay? And we plot it out. Okay? The feature name is the name that we gave it, otherwise they don't know what to plot. So, this is a tree, right? So it's very simple. They pick up the odometer and LE, not the age, surprisingly. Okay. So if you want, actually, you can increase the depth to maybe 5. Maybe we see more fun stuff goes on. It's not running, there's one. I figure out why it's not working. But let's go back to this here. Should one. Maybe it's not big enough to include everything, but you have that right here now. Let me check. Is it right here? That should be all right. So that would be the model that we have. Okay, is the tree is there. Okay, so what we want to do is to see the problem of regression, right? Because so far we only said the maximum level is the parameter we set, okay? But very often the problem is overfitting, because when you take the data to the real world, it's like doesn't fit very well. So there's actually 3 in the textbook mentioned. First is you require, when you have a cut, you have enough number of data in each divided part, right? After the cut, you can only have 1 data left, right? So in the very basic toy model, which violates this is, remember, the beginning of this example we have is we have 1, 2, 3, 4, 5. And the left note actually have only 1 sample there, 1 and 4, right? So the first rule is I cannot allow this to be too small, right? Maybe at least 5 sample point, but this one cannot be doable. But usually you have to set some minimum requirement for each node to be there, right? If this is too small, then you just stop. Say in this case, you don't actually do anything, right? That would be the first idea, okay? The second one would be what we call the imperative threshold, which means that if I do an cut, okay, the mean square error is not reducing sufficiently large, the threshold, okay, then I don't do the cut. So if I do the cut, doesn't improve enough, the RMSE does not reduce to my desired number, I'm not doing the cut. Okay, say so for example, I do this cut, if my RMSE doesn't reduce by 10,000, say, okay, then I'm not doing anything. Not do the cut. So it's a minimum, it's a improvement required if I have a more complex model, right? So if I want a complex model, I want the RMSE reduced by that number, okay? Now, of course, these things can be used cross validation to see what is the best, okay? And the next one is the idea that is slightly a little bit more complicated is what we call the pruning. Okay, it's the tree, you cut it out and let it grow again. So what does that mean is you grow a tree, you have the tree there, and then you calculate the, it's a little bit more complicated. It's like you just take away a particular branch and see how the overall improvement works. Okay, if the reduction is sufficient, if you omit that branch, it doesn't harm that much, you just cut it. Okay? So it's a slightly more complicated idea, but you keep growing and you cut this branch. Okay? Suppose you build a complicated tree and look at this level, actually it doesn't need it, and you just forget about it and keep going the tree. So every time you grow, you just check. It's like, before it's step by step, right? It's a linear development of the tree. But now I grow the tree. At some point I look back, is it some of the branch I can cut it out? Right, because up to level, if I do, say, in the level 1, I base on variable X, level 2 based on variable Y, level 3 may be based on Z somewhere, right? But maybe once I do the cut of Z, actually I can forget about Y. So I can cut there and regrow again. So there will be something, it's a little bit more complicated. Even the book doesn't say anything, right? The book say, oh, okay, there's something there. It's very complicated. Even the books are very complicated, right? So yes. So, but when you implement, it's very simple. Okay, just say one parameter to there. Okay. But let me show you this part first. Okay. So instead of maximum depth, I would require the following. Minimum split means every node at the end I have at least 20 data points. And impurity, I want it to, if the cut doesn't reduce the RMSE by this amount, then I'm not doing the cut. Okay? So that's what I do. Okay? Same thing here. Okay? That is, I add the minimum sample, I add the minimum impurity. I have criterion square error. Actually, I don't need that point. That is because of the latest regression tree is not based on RMSE, it's based on MSE, but the same thing, right? Because the root mean square, the mean square error are the same thing. Square error is just based on the MSE, but not the RMSE, but the same thing anyway, right? So you can fit that tree there. So let's fit that tree. And then we plot at the same time, so there's no need to waste of our time. So this is our tree, right? Looks a little bit more interesting, more fun, right? Because you can see once you do it, it stops here, right? Here stop, right? Because the data may not be enough sample if you look carefully. The sample size is smaller, so you just stop some, it's 42 here. So you just, once you split, then you can't go further, okay? Probably it's not big enough, but you can have fun by looking at this, run around this guy. maybe you want something, maybe height is longer, I don't know. No, look better. So it looks like this. Okay. So this would be the model, right? And of course, by construction, we don't care about how the tree looks like, right? Because with the prediction model, right? So we care about is RMSE, right? Which we'll look at that later. But this is the model we have at the end, right? We can plot the tree like this. Okay. And now, if you use a more relaxed criteria, you will see the tree will be very big. So the problem of this, of course, is in advance, you don't know what number to put, right? So that means that we need the complexity parameter to help us to cut the tree. So usually the way to do is you don't put this too strict, you put a low number of that, and then you cut the tree like the pruning. So, but let's show you how big the tree can be when you put a more liberal number on this. Okay, then you should see a super big tree there. Okay, you will see a big tree. Oh, I forgot to write the code of the tree code there. So if I try to write the tree there, take some time to run because of I allow a very complicated tree. You can see, whoa, it's a huge tree, right? So it's amazing tree, big tree, but probably if you put in practice, you will fail miserably because it's too complicated, right? So what I just said is, you don't want to fit this particular tree. Rather, you would want to use a CCP alpha. Okay? And CCP alpha is how complex the model is. It's like exactly the alpha when you do Lyso regression, right? And higher the alpha, the less complicated model. Right? The more simpler model, higher the alpha, same as the Lyso regression. Okay, and how this alpha change the graph is out of our scope. I mean, if you want, you can check machine learning textbook. I mean, there are many what it does that mean directly. But I think for our class, because the textbook even don't mention it, I don't want to bother you with that. And because you learn it in the machine learning class if you want to, right? And not everyone will go to machine learning class anyway. So, but this is the control. So you will see the code same, but I have this guy, okay? And this one will help us to make this monster to be a more reasonable one. Okay. Let us keep this monster under control. Okay, when you run it, and you will see the monster reduced to this one. Okay, so happy, right? Happy, right? So this is the model. Turn out to be the odometer, the real age matter, right? Not the actual age of the car, right? So this is the best model you can get here, and that's what we have. Okay, and so last but not the least is we want to look at how important the variable is, because the tree can't tell you which variable is good or bad, right? Then the question is, we want to see if we have this variable, how much our FC has been reduced by that, okay? Is that how important the variable is, okay? It sums up to 1, right? Because we take away this, variable, right, the RNS will expand, right? So, so that is what it's doing. So use the tree number 3, okay? And we have the function called feature importance, okay? And we sort them out, okay? And change the percentage, okay? And then you can see how important the model they are. So the importance there, and here I sort them by the importance. We sort them from the most important to the least important. Okay. And then I draw a horizontal bar based on the percentage, and the ticks are based on the names, okay? And once I do that, you give me a very nice diagram, okay? And that concludes the regression tree we have, okay? So this would be the diagram we have, is saying the age is the most important, the odometer is second most important part, okay? So this is the graph, okay? So so that means the age is the most important. Yeah. So I guess maybe there's some issue with this one, but I'll check it out. But this is telling us how to do the job, okay? And here we see a final remark for our regression tree. First is we have a model that we don't specify the whole thing with a top-down approach, right? We look at the model has empty and then we build it up, okay? And then we don't need to specify the square. The model will do it for you, and it's extremely sensitive to extreme value. If you add something, then probably things will change because you look at average of the group, right? So if there's one value that is extreme, then your model will break easily. Okay? So that's why you look at the textbook, they always tell you that the regression tree by itself, usually you don't use directly. Okay? The one actually used is random forest. Okay? But of course, if you have a lot of data, you can still use a tree, right? Because a tree or by construction actually tell you a lot of stuff, right? As long as data is not too extreme, you have a lot of data there. Okay? One extreme value doesn't change, right? So still it's not too bad, okay? Or the only bad part is the black box model, right? Right, because like the minimum impurity, the minimum depth, the maximum depth, right? Minimum sample split, those are parameters that you have to calibrate. And this hyperparameter, right, or tuning parameter is not something that you have economic meaning, right? Just there's no domain knowledge. There's no bets, then this is it, right? So that's a black. It's not so good part. But after the break, this is a compare contrast. I'm not going to go about that. But after the break, we want to go to random forest, where again, don't worry, the code is also very simple. Just one line of code. But we'll tell you the story behind what is it. Then this is the random forest. Is usually put in the production, right? The tree is basically gives them idea what's going on there, right? But the random forest is the one that we'll use it. Okay? So let's have a break of 15 minutes, and then we will resume later. And so in case your question, you want to leave your comment, feel free to do it now. Okay? We'll resume at 11:30. delay 做28，几号？好的，6号。 So here comes the very last session of what should be covered in the exam, right? So after this, you should enjoy the class, right? So this is the very last part. Random forest. Don't worry, the code will be very simple, but we will be seeing something more interesting, okay? But this is the code that you should know. So in the machine learning, there's an idea that we call ensemble method, which means that we are going to combine results from different models. Instead of one, we have multiple models, okay? And the problem why we need multiple models is because one model tend to be overfit, okay? Because overfit means, as we said, right, you fit too many features there. So it looks nice when you look at the data, but when you take into production, doesn't look very well. Even you have to make it more simpler, okay? So how do we do that, okay? We will rely on the idea that we call the bagging, okay? Which means the bootstrap aggregation method, okay? The idea is the following. So the data there, okay, and then you bootstrap the data, okay, and means that you, based on data, you create multiple universe. Why is it good? Because once you do that, you have multiple universe. It's very likely that some outlier would not exist in every data point, right? So it means that the outlier effect will be less possible because you create multiple universe. Second, then you will grow different tree, right, on different universe, and then combine the rule, that will be the bagging, okay? And this part is called another rule, which is in the advanced topic, it's called boosting. You also boost the data, but what different is, it is a little bit more complicated, which is out of scope. It's like you divide data into many universes, right? Bagging is you have 3 separated in different universes and average those out. But now it's different. What you do is, in the first universe, you build a tree, okay? And use the second universe to cut the tree there and grow again. And you cut it and grow again, okay? There's only one tree there, okay? And the first one is the most simpler one, right? The second one will be more complicated one, right? Because you base on the first tree, look at the second universe, whether you cut it or grow again, and keep doing that, right? So you start from the one tree and you keep growing, right? Of course, it depends on the first tree you grow, so that's why you would, it's very complicated, right? You have to grow, this universe will grow this in this way, go other way, so it's just a more complicated one. So that's why this one, if you try to do it, say, if you run a random forest, probably you would take 10 minutes. But if you do this boosting, probably take 1 day to do it. Okay? So that is why something we're not covering here. Okay? But we will talk about that a little bit, okay, if you have time. So as we said, the random forest has, I cannot maximize, why? Is the following. First, you would have different tree, right? Different data set, right? And then you would go to tree, okay? But there's one complication there, is decorrelated tree, which means that you would not fit the model based on all variable. You would randomly pick up number of variable to fit it, okay? Why is it we do that, right? Why we don't use all variable there? It's because the fact that there may be one variable that is too strong. It's very useful variable. If we have k different universe, you may always pick that variable to split. Then all the tree is very similar. Then you don't learn things. If you randomly pick up variable there, right? In some tree we will have that variable, in another tree we will not. Then we just pick up all the small feature, because the small feature is very important, right? Because we look at, beside the important feature, we want small features. So that's why this is a very important step. So, and then we average that, okay? So to repeat, what we're doing is, from data, you create k different universe. First step, there's a random part there. The second random part is, each universe, you just pick some variable to do prediction. And average them out, this is a good one. Okay? Is that clear? Just like the old story of Chinese, right? It's a bunch of blind people try to touch the elephant, right? Different part elephant will tell different part of the thing, right? Right? You know the story, right? I mean, different part will reveal different thing, right? Some people touch the tail, some people will touch the foot, some people touch the ear, right? Different people tell different thing, right? And that is very important, right? Because you would really want different people touch different part, right? If you keep all the variable, you always touch the same part, right? So that is the main idea behind, okay? So that means that there are many variables to check the random forest, but the book would suggest that these 3 are important tuning parameter. The first one is how many tree you want to do, means that how many universe you want to do, and this variable k or the t is 500, so you create 500 universe. Okay, that means that you are actually fitting 500 trees, so that's why it takes time, right? And you have to control how many variable you want, and the type of split. So basically you want the square root of the variable that you want to do, okay? And the last one is when you stop, okay, is how many observations you need, okay? So that is this 3 parameter there, okay? So this is a slide that's trying to show you that running the random forest is very simple. I'm not using this code, but this is just the idea how being done. But let me look at this is, so this line is creating the data by itself, so you can forget about it. This is test string split. You can forget about it. But I think the main part to run the random forest is guy only. Okay? Random forest is guy only. Okay? Here it tells you how many estimator you want for each tree, right? And then the depth there, and then that's the fit, okay? But that will be the main thing is the random forest, right? And then the fit, right? This is the main line there, okay? But now let's directly go to, this is the model, but I'm not going to show that to you to save time. So to save time, I directly go to this model hotel, the Airbnb data, okay, which we covered last time. We want to show you how the random forest do, okay? So very quickly. And because of time, I'm not going to copy the code and run it. Okay, you can run it because this is the only part that we don't have time to run it with you, but you can check it out, okay? I'm sorry that I cannot copy and paste because of time constraint. But what we do is, sorry, this slide is not the most update when I update a little bit. So I would do 30 number 3, okay? And then I would do this, the bootstrap, and then I would calculate the number variable and so on and so forth. Okay, let's run it, okay? Sorry, this is not the latest version of slide, but you can see lumpy and panda and URL and run that part. This is supposed to be okay. And I check how many missing data, and I drop the data without the price, which you know already, and fill the number of the bed by accommodate, and remove variable that we don't have X, okay, and fill in the number of bedroom, creating flat for missing data, fill the median, fill the review, and there's a new thing there, is a missing per month, then how we do that, okay, and some other cleaning of data, okay, and then I do the test training split, okay, and then this is the basic model I have, all the variable there, and the review, amenity, review there, okay, LISO there, okay. Now let's do the random forest, okay. So you can see the model after I clean, okay. It's very simple. I tell them how many estimator I want, and I guess the important part is this guy, and this guy, right? And how many estimator you want to do each time, right? When you, if it's you fit, you want how many variables you want, and this, something that you want to do is -1, which means that because random forest is very time consuming, so try to use all the power when you run this -1, okay? If you say 1 core, then it take a long time because you want the because remember random forest, right? You create multiple universe, you fit a tree in each universe, right? And that means that you want -1, right? So that is the part. Okay, you take some time to do it. Okay, and the other thing is, okay, in this model you will be looking at maximum feature and minimum split. Okay, the thing is you would want to do what we call the grid search CV. Okay, which we could have done that in LISO, but the LISO CV have already did that part, right? Because I said LISO CV also you can do the grid search, it's actually behind like that, right? Because look at the alpha, right? Which alpha is the best? Okay. Here we have two things. First is how many minimum sample split is, whether you split, how many data you have, right? And there's a maximum feature. Is how many maximum feature, because you pick number of feature there, right? So that would be also there. And we use the 5-fold CV, right? So this means that you will have 1 out of 5, that will be the 20%, right? And that you run this, then you pick up the best random forest model you get, okay? And if you try to fit the model, right? This is based on X and Y, they fit the model, right? Because so far we don't have the data, right? Look at the predictor there, you run the model, and you will see, indeed, doesn't really matter how many nodes you want, how many variables you want, that will be the end with the same. Okay? And you look at this ORS, look at this particular data. ORS has the RMSC 48, and the random forest gives you 44. So it's 10% improvement. Okay? I think it's large, right? If you improve 10%, your estimation error is a huge thing, right? Because the model, right? There's a model, it doesn't fit everything, but that is a very interesting idea there. Okay? So you can see the main code is this random fit here because this is the grid search. So this is the only part that is slightly more complicated. You have to decide this is the tune part, right? Then you put that in. Okay? And if you don't write this thing, then they will just pick up whatever is default in the system. There's a rule, if you don't put this in, you just feed the random forest, then you let the default value to be there. Okay? There are many things you can tune, but this is the thing that the textbook suggests you to tune it. Okay? And is that okay so far? I think this is it's nothing complicated, right? Because it's just, the code is just like, okay, you write all the clean the thing. This is the equation I want to do, okay? And look at this, I don't have any square term, no interaction. Because random forest, I don't need that. So this is, I include all the basic variable there. Okay, I don't need x1, right? x1 is interaction, so I don't need that part. But the problem of the random forest is, okay, I got this number, 44.5. If I run all this crazy code, this is right, something like that, right? But the thing is, okay, what do we know about the model, right? It's a black box. So we can plot something we call PDP, okay? It's very similar to the idea of the coefficient in the regression. Okay? So the idea is, if I change x by 1, how my y changes, right? If you run the regression, that's the coefficient, right? But this one is a complex model, right? So you put in the computer, you give me the value x, I change x by 1, or even smaller number, and put in the random forest and see how the y changes, right? You will do for every variable, okay? So that is called the partial dependence plot, right? So just like, same as scatter plot I have drawn many times, right? But this is way more complicated, okay? To give you some idea, what you will draw at the end is something like this. Okay? You look at, if 1, how many people there? 2. So this is a kind of graph you draw. Okay? The PDP plot. And the The other is I said, right, the variable importance, which we have done in the regression tree, right? You take out that variable from your model, right? Do the same. Do you see how the RMSE reduction, right? So that is the other one, right? So the variable, I'm not going to do it, but you can run this code, and this gives you this variable importance, okay? Like this wireless internet is the most important thing, right? Second is wheelchair, so on and so forth. I don't know why it's the case, but this is what we get here, okay? And these are the example there. Okay? I hope that's okay. I run a little bit fast, but I guess these codes are, at this moment, I guess you can run it by yourself without any issue. I mean, I guess it's good to leave you something that I don't go over, and because you will do it in your assignment as well. So I ask you the assignment, you will run a random forest. And then you run me the variable importance, okay? This code, you can just adapt your code to what you have seen here, okay? So I want to draw your attention to the final outcome of this particular example, okay? And if you see here, okay, you can read, basically forget GBM. GBM is a very complicated model, so you can focus on this. First four, okay? You will see when I run ORS, it's 48, right? And when we run the LISO, that is 46.8, okay? And then if you run the regression tree, it's not so good. Not surprising because it's subject to outlier, right? When you really do the validation, then it can perform very badly, right? But random forest, not surprisingly, perform better than ORS and ISO, right? If you do appropriately, right? So it does suggest that, okay, if you really want prediction, random forest win, right? But of course, you may say, okay, it wins. What's the price of this, right? Because it's way more complicated, right? It wins, but we lost the interpretation. It's just black box, right? And the drawback is it will take 90 minutes to run a random forest compared to like in 1 second or even 10 seconds or so, right? Or 12 seconds, right? And something like this will be much faster, right? And this is an important graph, right? Showing you the comparison of 4 different methods we learned, right? If you ORS, everything is by hand, right? If you which variable to do, whether you want square or not, whether you want interaction, this 3 is done by yourself. Okay? You have to know which to interact. If you miss them, then you will fit very badly, right? Because you forget those, then it doesn't work very well. But the good thing is, all the coefficients you can interpret very easily, right? This increased by 1, this is increased by that much, right? This is a very clear idea what the beta is. And when you LISO, right? One thing that is, you tell them everything there, but you select the variable there, right? You tell them the most complex you can imagine in your head, right? And it's good, right? You can still have interpretation, right? The coefficient is still can say something, right? Because it's just like increase x by this, beta increase by that much, right? There's somewhat that, right? But the problem is still interpretation still have something, but it's not clear why this variable pick, this variable is not picked, right? Because it's the prediction tell us, right? But still you can say something about the coefficient, right? Still you can see which one's bigger, which one's smaller, right? The bigger the coefficient is more important, that's it, right? Still can have something to say. But when you go to regression tree, okay, then of course everything become automatic, right? And looking at that is also easy because you can go by tree, right? Can see what's going on there, right? Which value, which part, right? Although you don't know why it cut in this way, but you also can say something. Also very fast, right? But lastly, look to random forest, then it becomes very difficult, right? Because you build different universe, and you fit different tree each time. So why add this? Maybe result of this tree plus this tree plus this tree, right? Unless your human mind can understand many different trees, otherwise it's very difficult to say anything. Okay, I have answered, but I don't know why it's the case. All right? So it's a little bit more difficult, but this is a better solution. Just like ChatGPT or LLM, right? Because like you don't know why it's true, but it's there, it works, right? Whether you like it or not, I don't know, but it works. It works, right? You don't care why it works, right? If you care why it works, there's a problem. Then you want to know, right? But if it works, then works well, then we don't ask the question because we want to do prediction. If your ideas understand what's going on there, you'll be the subject matter of next week, right? But if you just want prediction, I just want to predict as good as possible, random forest usually is the way to go, right? But if you care about interpretation, you want to learn more, you do ORS, right? It depends on the scenario, right? If you have very limited number of data, not many columns, ORS, you don't think twice. ORS the best, the simple model. If you have a lot of columns, then maybe LISO, right? You know what's going on, but something I don't know too much, right? Like the Airbnb case, right? Or the hotel case, you know something. There are a lot of things I don't know. There's small feature I don't know. Not very important I don't know. Then LISO, right? So you know a bunch of things, but you don't know something. LISO you can tell. And random forest is why you have to rely on computer, because you know nothing, right? You don't learn anything. So let the machine learn it for you. Right? So it's just like when you know things, you should do ORS, right? If you don't know, then you rely on the machine learning. Right? Just like ChatGPT, right? If you use ChatGPT or AI, if you know, then probably you shouldn't ask AI, right? You just look at the book, then that's done. Look at the Wikipedia, look at the encyclopedia, then that is the end of story. Don't ask the ChatGPT, right? Because ChatGPT may not give you the right thing, right? That's like the question, look at the textbook, right? Don't look at ChatGPT, right? It's not the time to look at ChatGPT. But if you don't know what you don't know, right? Or you don't know, then ChatGPT or the random forest is the best. I hope it's clear what we're doing here, right? Because that is the assignment. The assignment 3, which I will probably release next week after the TA check or everything. We ask you to do all 4 of the things, combine to get the last assignment. Then you have a good idea of how to run the code there. Although the random forest, I pretty much skip a little bit, but I guess at this point of moment, you should be able to run it easily. I mean, it's okay. I don't go for line by line to copy and paste. Right? You can do that by yourself, and that would be the model we have. Okay? And you can see the last one is actually the most best one, right? Even a 0.1 drop, okay, is much better one. It's very difficult. Right? As I said, it's an improvement of random forest, right? It's you build a tree, and then you grow the tree based on the last tree, and you keep growing that, okay? And that means that the knowledge from one tree can be extended to other, right? Instead of building independently, the tree is built sequentially, so you can combine knowledge from different universe rather than just simply average out. So it's a much more sophisticated way. Of course, you need a computer, right? So that's why they explain why it's very similar to ChatGPT idea, right? Just keep growing stuff rather than learning independently, right? So it's just like a more complicated learning approach, right? So you need a lot of computation power, right? And the improvement is not that much annual, right? But it becomes so much complicated, okay? But of course, if your computer is very fast, you don't care, right? But I think I still, in practice, people basically use ORS LISO or random forest, right? Very few people use this one put in practice because not too much difference anyway. This is some improvement, right? But it doesn't worth the time, right? It's how many days you need, right? 1 day, right? More than 1 day. Okay, so that's pretty much marked the end of the material that we cover in exam. Okay, but what we want is to very briefly preview what we're going to do for the next 2 classes. So far we only care about prediction, but for business, right, besides prediction, which is important as well, but there's a reason we want to understand causality. Why change in X need to change of Y? Why we want to do that? Because suppose X is maybe a marketing effort, or how we change the feature of the website, right, or change some switch. We want to look at how traffic change or how the sales changes, or something we care changes, right? The prediction model cannot tell us about that part, right? If we want to spend money on doing particular change in the business decision, this is where we need, okay? And in particular, if you remember, right, just a very simple example, just to illustrate why we need that, is, but suppose I want a regression, right, which is say y equal to alpha plus beta 1 and beta 2 and so on and so forth, right? Many things, right? And this regression, if you care about prediction, you can add as many as you want, add the square, whatever you like, right? You can, whatever model you fit, as long as you fit the RMSE is lowest, then you're done, right? Means that there's nothing related to the real world is important, right? So then you don't expect this thing has anything related to the real world, right? Because here we discard anything we know about the world, right? So what is important now is we need to look at the world that will guide us what should be there, what shouldn't be there. Okay? We do not put everything in there because it helps prediction. We only want to put the thing that should be there. Okay? And that is the first part of the causal identification, is we have to draw a map of causal map, and it will tell us what should be there and what shouldn't be there. That will be the goal of the causal analysis. We'll define causal effect. So that will be the chapter 19. The main job of the next class will be telling us why caused by X and Z, when we should include Z, when we should not. Okay? And depends on many things. And the problem is in the real world, that is a lot of things is hard to say. Okay? So to derive causality is very complicated. So luckily, the chapter 10 we will tell you there are many ways to do it, but we focus on one particular way called difference, because there are many ways, but the time only allows us to focus on one particular way. It's called difference. This is how we do in science, in experiment in the lab, right? Why, say in experiment, like medical experiment, right? Why we say a particular medicine is useful, right? Is we have the control group and the treatment group, right? And one group patient is given the medicine and see before and after how it works. There's a difference to compare. After taking medicine and before, there's the first difference. But it may be due to the effect that he eats something, right? The placebo, right? So that's why we give him some pills, but has no impact, right? The control group. And then we compare the difference between the treatment group and control group, and that's how we see the impact, right? The reason behind is you need the control group to capture change in the environment, right? The main idea is following, right? Suppose you have the website data, right? And you only capture it today and tomorrow, right? You want to implement the intervention for some group but not the other. Then you can compare, right? But the problem is today and tomorrow is a different day. Tomorrow is Saturday, right? Today is Friday, and people behave differently on Friday and Saturday, right? And so that's why you need to control that impact. So that's why the most important part is called different analysis, and this is, I think, you look at many of the frontier research or look at how people do it, different is the way that you identify causality, and that's how you do in business as well, right? You would suppose you want to see the marketing campaign, or you can see or how the program changes. You have the beta version of the software, right? And beta version is randomly give to some of the people, and they test it and see how they perform, and in parallel compare to other group that doesn't receive the beta version of the model, the software, and see how people engagement is different. Looking at the beta version, non-beta version, right? And that's what we're doing there, okay? Of course, there are many ways to do it, like regression continuity, panel data, many ways to do it, but we focus on the one that used most often business, which is selecting some group of the customer or some test agent and apply it, right? Look at the window, right? They have the experimental program, right? People have the new version of the window and ask them to test, right? And see how is it improving or not, okay? So that's the main idea. As I said, next class will be very quick because if you really want causal analysis, actually will be a very deep thing. I mean, I would say if you have to do an expert in this, have to study a Ph.D. and basically many econ Ph.D. basically do one thing is identify stuff. It's doing this, doing different. They make living. You have to learn 5 years to become expert on that. So we can't make you expert in one class, right? So we're just telling you one particular tool and one particular way to do it, and that is the most useful way. And I think that would be the main idea that we do next class. So after next class, it will be a presentation, okay? So I hope that you have already signed up for your presentation slot, and then this is a slot, and then if you haven't write a topic, then we do it, and then the group. I think what we will do is we will randomly draw the number from the group, then you present. Okay, the order will be decided randomly on that one, and then each group member will present 2 minutes. Sharply, we'll control the time. So, and then you will vote for who is the best presenter, right? And also best group. Okay, or the most interesting will give you several prizes, right? For this class. So that make sure that you present and you make sure your name is well known. Otherwise, no one will vote for you, right? You want to be the best presenter as well. So I guess we are 58, right? So probably everyone present 2 minutes. Okay, that will be everyone has to present because I will give grade to everyone who present. Okay, so you also vote for the best presenter in the class. Okay, okay. So I will see you next week. Bye bye, and have a nice weekend.